actually on a very atomic level, a circuit that does 16, 8, and 4-bit math in LNS versus a circuit that does, same shape of a matrix multiply grid, but just does everything in floating point. There's actually much more than a 5x saving. It can be as high as maybe 10x or so, but because especially in 16-bit, it's pretty insane how much one is saving.
Hello everyone, this is Sally Ward-Foxton with EE Times. You're listening to our AI podcast, AI with Sally. This episode is brought to you by our sponsor, Tensordyne. Tensordyne hit the headlines recently when it unveiled its data center inference platform, built around a custom engine for the logarithmic domain that promises dramatically higher performance per watt than conventional floating point hardware. In this episode, I'm joined by Gilles Backhus, co-founder and VP of AI at Tensordyne. We're going to explore the mathematical foundations behind the company's approach, why it believes logarithmic number systems are ready for the data center, and how its recently announced Napier platform aims to challenge conventional GPU architectures for LLM inference. Here's my conversation with Gilles. Okay, Gilles, welcome to the show.
Hey, Sally, thanks. Thanks for having me.
So let's start with the origin story of Tensordyne. I think you're one of the original founders of the company, of Recognize as it was then. Tell us, whose idea was it to start a company and how did that happen?
I think there were multiple people who in the end came together, who kind of came to this idea of developing inference-focused, high performance, but optimized AI chips. And in the end, so the starting team was fairly quickly 8 people. Sounds a lot, and but I guess not everybody was technically a co-founder or so, but we were 8 people in the beginning, and a lot of these people are also still in the company. And a bunch of people came from the world of vision, which obviously was also at the time, especially the bigger market than language processing, which of course today is a bigger market. And yeah, just they discovered there's not really an AI chip in the market that is both efficient and very performant and can operate on very high resolution camera data natively and detect objects and things like that. So yeah, object detection, semantic segmentation, image classification, those were kind of the things in the beginning. I personally I started 5 years before we started the company working on real-time AI on FPGAs. So I also came from that angle, and then yeah, that's basically how a bunch of random people came together and said, okay, let's build a very high performing AI chip for inference, but based on this new logarithmic math. So that was actually there from the beginning to save a lot of power and make the chip also smaller and so on.
So I know your whole technology is based on this logarithmic math. The logarithmic number system isn't new. It's been used in DSPs. Like if people are familiar with DSP programming, they might be aware of this, but maybe you can talk kind of high level first about, what is LNS and how do we apply it to AI?
Yeah. So LNS, first of all, just has that basic idea of, instead of representing numbers like integer would, where, well, you have an integer and a fractional part, or how floating point represents numbers, which is you have an exponent, it's an integer exponent, and then a mantissa, which is basically 1 plus the mantissa times 2 to the power of the exponent. Let's just say you only have an exponent, but the exponent can also have numbers after the decimal point. So it's not just 2 to the power of 4 and 5 and 6, but it's 4.2 or even 4.27345. And the advantage from that is that you can just add 2 of these exponents and you have effectively multiplied 2 numbers. So what normally costs the most, which is multiplication, suddenly becomes what normally is the cheapest, which is an adder. But then then the real interesting stuff starts to happen. So you then have to convert that number, that basically multiplication result, back to a linear representation, Because most of the time, for example, when you do matrix multiplications, which are, 99% of what you do in AI, after a multiplication, you will have an addition or accumulation, which I guess is just a way to say there's lots of additions in a row. But either way, there's going to be an addition after the multiplication. So doing an addition directly in log space, pretty much normally, if you have, let's say, perfect math, would involve going from something in the shape of 2 to the power of down to just And well, how do you do that? Well, you take that number that you have, which is an exponent, you have to now calculate 2 to the power of that thing to get back to its linear state, which is, of course, extremely expensive, right? It's highly nonlinear, and it's not easy at all to do that. And so this is why then people said, okay, let's first discard this idea of doing it perfectly, right? Like, for example, through a Taylor series expansion, through some kind of multi-step thing that a CPU might do, where the longer you crunch the numbers, the closer you get to the result. So that obviously doesn't work, takes too long, and so on. And it doesn't really fit the whole vibe of having, 40,000 compute units on a chip and highly parallelizing everything and so on. So then the next idea is, and I think this is where people look more seriously at it, what if I do this log to lin and lin to log conversion with a lookup table? So number comes in, I have a table that converts every number perfectly, just read the result, and then boom, out it goes. Pretty much, what is that? It's a memory element. Maybe you can do it not as an SRAM cell, but you could actually do it as a just completely baked lookup table. Then you would require less area, but still, it would be a lot of area that you require on the chip, especially as you look at higher precision numbers, which for a very, very long time, I know today it's kind of lost its importance, but for a very long time, even AI chips looked at least 16-bit as well, to kind of have native support for 16-bit. And so then if you have a lookup table for 16-bit, it gets extremely long because you have so many different 16-bit numbers, obviously. So the lookup table would be huge. So then also that was discarded. But that actually, not too long ago, I still remember a few more targeted AI talks from big companies in the AI space who, as early or as recent as 2.5 years ago, said, we looked at it, and because of lookup table sizes, we discarded it. And what we did was we looked at the so-called Mitchell approximation. And there was a paper from 2016, a Stanford paper, that alluded to this idea, but they only formulated it and also just partially for CNNs, for convolutional neural networks, which were, of course, the dominant kind of neural network operator back then. And they basically said, well, the Mitchell approximation says the log 2 of 1 dot something is just 0 dot something. So it's extremely cheap, right? If you have a leading 1, you just throw it away, which in silicon almost means you let that wire die into nothing, and boom, suddenly you have its logarithmic representation. Great. But it comes at a cost. It comes at, well, it's an approximation, so as the name suggests, it comes with an error. And the error is not to be neglected. So what we did in the first chip, our 7-nanometer chip in 2022, was that we implemented this Mitchell approximation just as is in silicon. And that required us to do a so-called quantization-aware training approach, which means you have to train your already trained network for a couple of steps in that logarithmic math so that the accuracy of the network can go back up. Because first, if you just kind of switch on the log math in that form, accuracy goes to almost nothing or random performance. And then you kind of climb very quickly back up by just finally, fine-tuning basically the whole thing and getting back to that performance. So it was totally feasible. It's just not feasible with the network sizes we have today. Because nowadays, right, most people, they just use AI models. So the company that trains an AI model and the company that uses an AI model, two completely distinct companies. So you can't really expect someone to fine tune something like a DeepSeek R1 or so in our math. That would be completely impractical. So we had to improve the Mitchell approximation's accuracy and a bunch of other things to make it a pure PTQ play. So post-training quantization, which means now you don't have to train the network anymore. You just switch on the math and it completely happens under the hood. The user doesn't even have to know that it's log math under the hood, and it's as accurate or even more accurate than floating point, and it just works out of the box. And this is really now the state of in this Napier silicon generation.
So your secret sauce really is in both how you've adjusted the Mitchell approximation and the way you've implemented it in hardware, right?
Yeah, and there's a few other things we've done, which partially are also patented, so you could theoretically look into it online, I guess. For example, our two-stage accumulator approach. Yeah, and there's so many other tiny things that all kind of compound and accumulate. How data moves through the chip, how we've designed it in such a way that it's mostly or almost exclusively microcode controlled. Data flow architecture, basically, where there's almost no CPU involvement. So it's very pipelined, it's very parallel. And now when we look at kind of the execution traces of compiled AI models, you can see that it almost looks like you really have to zoom into it to see even the tiniest areas when the, matrix multiply grid is actually not doing anything, because it's almost always busy. And so we paid a lot of attention to these kind of things as well. So it's not just log math, right? I'm going to be honest here. The log math is very easy to sell as a kind of catchy innovation, but no, it certainly isn't just that. There's so many other great things that our co-design teams, our silicon engineers, our AI engineers came up with. And
maybe people are listening to this thinking, oh, the log domain, the log math sounds a little frightening, but if I'm using a system like Tensordyne, from a software perspective, they wouldn't even see that, right? It's all kind of abstracted away.
Yeah. So first of all, I have to say, I completely get it, right? That people are a little bit, oh, wow, is that still accurate or not? Right. And we can't expect everybody to be an expert on the theory of log math either, right? Because actually what's not funny, but almost ironic is that if you look into the theory of representing numbers on a log scale, it is actually more accurate than floating point because it has the smallest maximum error for any number or for any given number of bits. So, but yeah, of course, we can't expect everyone to just accept that or internalize that or whatever, right? And even then, right, they know that every math implementation has its own little special things like the accumulator. So even if it wasn't that log scale representation, we have to prove anyways that things run accurately. And so yeah, we do that. We also have an emulation environment that is bit accurate, so you can run workloads in there. And of course, we've done that like day and night for years practically before we've gone to this tape out now. But yeah, it's now really completely hidden and under the hood, because even the microscale application, or basically applying a microscale to a group of numbers so that you can move around the number range that it represents, even that happens dynamically, because our vector processor on the chip, it can dynamically on the fly look at those, for example, 32 numbers. It derives the min and the max and then applies our scale, which we call exponent bias because we think in exponents, dynamically. So so that's for the activations, for the intermediate signals, and then the weights, they just get similarly compiled ahead of time by the compiler and quantized that way, and then those numbers get flashed into HBM, and then that's the weights we use. So it's completely hidden away from the user. Yeah.
On the other hand, if I was coming from HPC, or I was used to writing my own kernels, or maybe I have experience in DSP and I'm confident on LNS, can I get access to the lower levels of that stack? Are you going to open that up for users?
Yeah, absolutely. Totally. If you want to, you can set every tiny little exponent bias yourself. You can say, let me run this layer in, 4-bit weights and 8-bit activations. Let me run the next part of that layer in 16-bit. And then, yeah, you can absolutely fine grain, hand tune every tiny kernel in terms of our numerical precisions that we support. Yeah, you can absolutely set all of this yourself. Yeah.
Yeah, so the maths is one thing. Taping out this big chip is another. And I know you said this isn't Tensordyne's first chip, because you previously were making an edge chip. Should we think of the edge chip as a first gen and this is a second gen, or did you completely go back to the drawing board for the new chip?
Yeah, thank you for this question. Hopefully the whole world listens to this, because maybe I'm finally going to be able to bring some clarity into all of this. So the only thing that the first and the second chip have in common in terms of, let's say what kind of secret sauce lives in there is really just that log math principle. But even that has evolved so much. Otherwise, everything is different. Okay, maybe the only other similarity is that we used RISC-V cores in both chips, which is great because we were already able to learn from it. But even then, the first chip actually had a open source RISC-V design that we didn't practically have to pay for. Now we have professional licensed RISC-V IP, so even that is very different. No, so it's a much bigger chip. It has lots of other things that the first chip didn't have. It has a completely different data flow architecture. It's very, very different. I think the only thing that the first chip proved very impressively was how ridiculously energy efficient log math can be. Yeah, because we were able to do things like a dual 8 megapixel stream in HDR, 300-meter range 3D object detection, and the whole chip in real time only consumed like 3 or 4 watts. It was actually really cool. Yeah, but no, other than that, it's just going from automotive to data center, which we pretty much did 3 years ago. Actually, our CEO just did a great post on LinkedIn on kind of that phase of the company. Looking back, it's a little bit of nostalgia, I guess. It was really almost more like a homecoming for us because so many people in the company came from the data center space. Like my co-founder RK, right, our chief silicon designer or architect, and so many other people actually came from companies like Juniper Networks. So it was almost like a homecoming, yeah. And thank God the math part was already checked. And yeah, what's maybe to note also, before ChatGPT happened, transformers already entered the vision space. So for the object detector nerds who are listening to this, you might remember things like, first there was YOLO, those kind of object detectors, and then suddenly there was stuff like DETR, which was, I think, the first, was it from Meta? I think it was actually from Meta. The first object detector that also impressively used transformers. And then there was from Andrei Karpathy, there was this great Tesla AI Day on YouTube, where for the first time they explained in detail how they're using transformers to almost magically cross-calibrate across multiple sensors and across multiple sensor modalities. Super cool stuff. And so transformers were already becoming a huge thing in vision as well. Oh, and of course capsule nets from Geoffrey Hinton, which everybody went crazy about. So we had already, even before ChatGPT happened, we had already begun with a new silicon generation where we completely redesigned the compute engine, not just CNN support, but also matrix multiply support. And also for the first time, not just weights with activations, but also activations with activations, because that's also a new thing, which from a data flow point of view was very important to kind of design in. So, but other than that, yeah, it's a very new design, I would say.
So the big chip that you have built that we're very excited about, you're going to do data center inference for LLMs, for token generation at a really big scale. And the key is power efficiency. Tell us, how much power can we save by switching to this LNS-based hardware?
Yeah. So in practice, I would say 5x. But right, and this can be explained on a more atomic level, I guess. Actually, on a very atomic level, a circuit that does 16, 8, and 4-bit math in LNS versus a circuit that does, same shape of a matrix multiply grid, but just does everything in floating point, there's actually much more than a 5x saving. It can be as high as maybe 10x or so. But because especially in 16-bit, it's pretty insane how much one is saving. Because in 16-bit, the multiplication is way more expensive even than in 8-bit. But yeah, on a system level, on a data center level, it's around 5x. But again, it would be unfair to say that this is all just because of log math, right? It's also because of so many other things. So why do I say 5x? Maybe even a little bit more than that, depending on the workload. It's because our box with the 72 nodes, you can compare that pretty well to a Blackwell Ultra rack. And our box is 30 kilowatts, and that box is 150 kilowatts. So that's a 5x. But actually, if we compare ourselves to a disaggregated data center of NVIDIA Rubin and Grok, then the saving actually goes up to 10x because we can do disaggregation within a single system and still achieve these KPIs or even much better KPIs than what NVIDIA Rubin and Grok showed. So there the saving is actually 10x. So let's say on a data center level, 5 to 10x maybe.
So can I also save money, Gilles? And can I save money and power at the same time?
You will definitely also save money because you just have to buy less hardware, I guess.
Use less power, yeah.
And use less power, yeah.
Yeah.
Power is expensive. I mean, it really depends on which country you're in. If you're in Germany, then yes, power is very expensive, so you're going to save a lot of money there. If you're in a very optimized setting in the US, then power might not actually be a huge part of your bill. If you look at the entire total cost of a token, yeah, but. Yeah, for sure. Also savings on cost a lot. Yeah.
What about raw performance? If I am primarily interested in speed, tokens per second per single user, for example, can I save power and save money and have faster tokens?
The answer to that is yes.
Thank
now
you.
it's probably starting to sound too good to be true, but let me try to explain it. So this actually now has to do a lot with something we didn't talk about yet, which is our fabric. So I think we're next to NVIDIA and maybe the new AMD Helios racks, the only other company that has that true any-to-any 72-degree fabric, scale-up fabric. So meaning every one of our 72 chips are a direct neighbor of all other 71 chips. And that happens through technology that we have designed together with our partner HPE Juniper Networks, who have really great technology when it comes to that, and it's very low latency. And what that allows us to do is to parallelize workloads better than anyone else. So right now, if you took something like a DeepSeek R1 or I guess DeepSeek V4 Pro to take a newer one, or a Kimi K 2.7 or so, those mixture of expert networks, right? The thing you want to do the most is very wide expert parallelism. So ideally, maybe 64 or maybe 72, if that's a number you can easily divide through. Actually, the way we would do it, we would most of the time have 8 of our accelerators for prefill and then 64 of our accelerators for decode. And then you can have, EP64 and then maybe TP32 or TP64 for the dense parts of the network. And when you do that, you will normally, for example, in an NVIDIA system, you will be bottlenecked by communication. Because for every little token that you generate in these mixture of experts, you're going to have hundreds of communications in between the chips. Because for every layer of an MOE, and DeepSeek, for example, has 60 layers, you're going to have most likely 4 communications. And so 4 times 60, you're looking at more than 200 communications. So that's literally what happens. And so even if the messages are tiny, which they are, especially at super small batch sizes, which you might want to do because you want to be really fast per user, right? That's kind of what you asked, like, can you be fast per user? You're going to have these hundreds of messages. And let's do the math quickly, right? When you have 200 communications, and NVLink from NVIDIA has a latency of roughly 10 microseconds. So 10 microseconds times 200, that's 2 milliseconds. That will, or rather like 2.5, let's say, 2.5 milliseconds, that's a ceiling just because of that of 400 tokens per second. You will not be able to go beyond that because of NVLink, even if everything else is infinitely fast. And that's exactly actually what you can see. If you go to NVIDIA's website and you look for their DeepSeek V1 number, you will actually see that they're not even getting to 400, but maybe like 350, 360 or so. So it's actually because of that, exactly. And because otherwise their HBM bandwidth and so on would actually be more than enough to go higher, much higher actually. So they're bottlenecked by that, and this is why they then had to go to Grok and so on. In our case, because our latency is literally 10 times lower, it's just 1 microsecond, because it's a very, very low overhead, super slim cell-based fabric. we're totally not bottlenecked. We're still actually bottlenecked by HBM bandwidth, even at these high degrees of parallelism.
I know the Napier server has 72 chips, and you just said you use 8 for prefill and the rest for decode. But to what extent did you pick 72? Because NVIDIA has 72 in one NVL72 kind of domain. What I hear from the market is that people want ever bigger scale-up domains. So I'm curious about why you picked this 72 number.
Yeah. So the 72 number came to us because we were trying to be as compliant as possible. We almost had to because of a certain partnership with a chassis provider and a fabric provider, HPE Juniper Networks. We had to align with a certain number of fabric lanes per board. And there were 8 boards in that chassis. That was a given. So now 8 times 9. So why 9 chips per board? Because that resulted in a very nicely dividable number given the fabric lanes per board. Because the board actually has 36 times 9 fabric lanes. And anyways, very often, for whatever reason, in the scale-up world, the base multiplier is not 8, it's 9. Very, very often. Actually, even Broadcom with their newer Tomahawk generations, they don't have 512 lanes anymore per chip or 1024. They now have 576. And so this is why it was 72 and not 64, for example, or any other number. But of course, once we, because it could have also been 144, right? We could have also just built smaller chips and put more chips there. Or maybe it could have been 36, just bigger chips. But we saw 72. Well, obviously, we immediately saw that this is exactly the same number as NVIDIA with their NVL72 systems. And we thought, hey, wouldn't it be nice if we had exactly the same number of nodes? Because then if somebody wants to deploy an NVIDIA and on us, basically the migration problem, at least they don't have to rethink their parallelization configuration. So that was a plus. Yeah, exactly. So yeah, we do hear this from customers that they're deploying workloads on more than 72 nodes nowadays. I think that problem needs to be dissected a little bit. So there's many different dimensions today for parallelization, right? There's tensor parallelization, expert parallelization. These two can also be combined in different ways. Then there's data parallelism, which is most of the time we don't regard data parallelism as parallelism. It's just basically you're processing multiple users in parallel on completely separate systems, but these systems are not communicating or exchanging data. Then there's pipeline parallelism, which is not very demanding because you just send a bunch of features from one system that did for the first n layers to the next system that does the next n layers. So it's not very latency or bandwidth demanding. Did I forget something? Well, there's disaggregation, which is also kind of a parallelism. And yeah, so those are kind of the 5 dimensions we mostly think about. So when people say they're deploying on more than 72 nodes, probably some of these dimensions are folded into that. When we think about a scale-up domain, we mostly think about tensor parallelism and expert parallelism, maybe pipeline parallelism as well. But yeah, it's not that demanding, so you can do it with slower technologies. But even there, right, I totally see why people would want to deploy on, for example, 256 nodes. Why? Because a lot of mixture of experts have 256 experts, and you want to go as extreme as possible. And so we actually do have a solution for that. We never talked about this publicly, but stay tuned for an update where we have a new or alternative version of one of our components in our system that effectively exposes our fabric to outside of the pod. And so now multiple pods can work together as one RDMA domain. And yeah, I'm not going to say more than that because it's still a little bit in the works, but it's actually not a huge change we need to do to the system. But yeah, that is basically our reaction to the customer demand of going wider. And then our next gen that we also already started working on, that's definitely going to have that in a very meaningful way. Yeah.
What if I wanted to use your racks in the disaggregated setup that I've already got? Maybe I've already got NVIDIA GPUs that I've already invested in, or GPUs from another vendor. It doesn't have to be NVIDIA. Maybe I want to put in some kind of decode acceleration to help those GPUs. So you just use the GPUs for prefill or split the decode or something. Can you fit into that kind of setup as well, Gilles?
Theoretically, absolutely. Probably we would rather be covering the decode side of things and not the prefill side of things because it's just a slightly better fit for us. I mean, again, we're pretty good at both, but I guess the decode is even better because of the fabric stuff I explained earlier. So yeah, totally. I mean, there's probably a little bit of manual implementation needed there, right? We would basically have to receive prefill tensors from an NVIDIA system through Ethernet, I guess. And yeah, but then it's totally possible. Yeah. So bandwidth wise and so on, and even latency wise shouldn't be a problem, right? Because that prefill to decode forwarding is not part of the auto-regressive loop yet. So it's, yeah, totally possible. So in theory, absolutely possible.
I guess I was thinking that it seems like compute is where you really excel with the LNS thing, and that's why maybe you'd fit in on the prefill side. But yeah, I guess not.
Yeah. No, absolutely. I mean, yeah, sure. If we run a network in prefill on 72 or 64 chips in parallel, yeah, it's blazingly fast. And again, even there, our fabric shines because if you want to do very high degrees of TP or EP during prefill, of course, you're still going to benefit from the low latency. Yeah. So no, absolutely. Definitely also possible, but I guess we're somewhat equally good at both, and so that's really the thing, right? Like we do want to coexist with NVIDIA, but not because we would benefit, or a user or a data center would benefit so much from doing disaggregation cross vendor, with NVIDIA and us or AMD and us, but more because we just realized the sheer reality that nobody will just tomorrow say, okay, let me build a gigafactory with only Tensordyne systems, right? We might be there as a vendor in 1.5 years or so, but obviously not in the beginning, right? Nobody will take that bet. So people will just, have maybe 80% NVIDIA, 10% AMD, and then maybe 5% Tensordyne, right? Just to be very realistic, I'm probably going to be beaten a little bit by our marketing people now after this. But yeah, obviously, I mean, it's important to realize that, right? Because most data center, most meaningful customers of ours, they will be looking at us not from are you an alternative to NVIDIA? Well, yes, they will be looking at that, right? But they're not going to say, now I only want to use you guys, right? But we have to integrate software-wise into a multi-vendor data center. And we want to make it so easy for our customers that with a single software stack, ideally they should be able to serve NVIDIA systems, our system, and other systems. And we just want to we want to integrate into that as easily as possible. And so this is why it's great that we also have 72 nodes, we also have HBM, and you don't really on any super substantial way have to rethink where you place your weights, where you place your KV cache. Yeah, we also support all the precisions that are supported on an NVIDIA system. So that was also a lot of times, in our mind when we designed the system.
Yeah, I mean, I think if somebody's thinking about changing from what they've got already, which is probably NVIDIA GPUs, or switching part of the workload over to something else like Tensordyne. Always over the years, we talk about like CUDA is such a big moat for NVIDIA. CUDA was so important. I mean, AI software stacks are getting a little more mature now, and I'm seeing people talking about converting CUDA code using AI, just feed it into AI. Do you support people if they are changing from NVIDIA or changing part of the workload from NVIDIA, or how do you help them with that?
Yeah. So it can mean different things, right? Like if for example, someone operates on a rather high level in, say, VLLM and just uses PyTorch only, that is fairly easy to support because that's such a high level description of a model that we can very easily transpile from that to our DSL. Then the next level would be, I guess, Triton kernels. If it's Triton, very often we can also translate that fairly straightforward. And this is also where actually we've seen great results from using agentic transpilation. But of course, sometimes you're going to have Triton kernels that were written by people with just NVIDIA devices in mind. So for example, a Triton level flash attention implementation, totally optimizing the hell out of that, or out of attention for an NVIDIA device, it won't make sense for us to directly one-to-one translate those number of kernels or that kernel directly, right? Like, so what we rather need is to detect that in the code and say, okay, now instead of that, let me use our implementation of flash attention and then replace the entire block with that. And this is actually where LLMs are pretty good at detecting these patterns and so on. So we don't have to hand build all of that. And then finally, if somebody's really implementing things on a CUDA level, yeah, I mean, most of the time when they do that, they're still going to have a higher level description of that same model. And so we might just ask them, either just rehamped implement everything, or maybe the LLM is going to help you a little bit in doing that. That's one way. And or go back to a higher level description of that same model. That's probably going to make all of this easier. And or just look at the implementations we already have on our Hugging Face Hub. Chances are the model that you want to implement is already there. If it's not something completely custom or, from a frontier AI lab. Of course, if it's completely custom and a kind of secret architecture, then yeah, you might have to re-implement some of these things. Yeah. But it's more and more automatable. And I would say the CUDA mode is dead. I don't think it exists anymore.
Okay, let's talk about the chip a little bit in whatever detail you can give us. I know it's a 300 watt chip, or 300 watts per package, but that includes 144 gigabytes of HBM. I know you offer 2.1 petaflops of FP8 compute. That is a really big number. This compute density is purely down to the LNS math that we were talking about earlier, right?
Yeah.
Can you tell us anything more about what's on the die, the compute die, apart from the new arithmetic units that you've got? What else is different?
Yeah. So there's also 16 RISC-V cores that I think I kind of mentioned earlier. They are mostly there for dynamically converting instruction templates into the instructions that will actually be executed. Because nowadays in AI models, you can't compile everything ahead of time. There will be dynamic things such as which expert gets called next, right? That is not crazy dynamic, because you will still know ahead of time how many operations will be executed, because if it's that expert or that expert, it's still going to take the same time because it's still going to be executed on that same kind of chip and so on, right? But then other things that might be dynamic are the batch size, the input length, the output length. So this is the RISC-V core's job to patch those sequences into the sequence, these instructions into the sequence. Other than that, almost everything on the chip is microcode controlled, meaning there's lots of different little control engines all around, like all over the chip, that will do things in parallel. So for example, if one chip wants to talk to another chip through RDMA, that again, no CPU involvement. If the vector processor wants to operate in parallel to the matrix multiply grid, that will just be part of the instructions, and that will be completely in parallel, and there's not going to be any kind of CPU cycles that you have to wait for or anything like that. I mentioned the vector processor. Maybe let me talk a little bit about this. So that guy is a little more numerically flexible than our matrix multiply grids. So it can also do other math than just log math, but it can also do log math, and it even comes with a lookup table. So if you have some super crazy math that you want to implement, then just use our lookup table. You'll be done with it. It's double buffered, meaning we design it in such a way that it will never be waiting for input being loaded into it. But there's a substantial, we call it VBuff, so a vector buffer that basically allows you to keep it always fully busy, as every other part in the chip. And then there's a bunch of read and write path circuitry in there, which allows you to, again, super on the fly, do things like matrix transpose or some scatter gather operations. Yeah, what else? There's a lot of SRAM on
There's a
there.
bunch of SRAM, yeah.
Yeah.
Because you can save space, I know, by being really compute dense, but how much more SRAM can you add?
Yeah, so we put everything on the chip that we wanted to put, and then we kind of filled up the rest with SRAM. Because when we designed the chip, it was really hard to estimate. Okay, do you need 32 or 64 megabytes per compute cluster or so, right? So in the end, it became 64 megabytes per compute cluster. We have 4 clusters per chip. Every one of those clusters has 12 engines, and every engine is 128 by 128. And then it gets clocked at a certain frequency, and that's how you get to the 2.1 petaflops. And then there's a lot of elegant design choices around how the SRAM can be accessed. So it's everybody can read in parallel and write in parallel, and But this is kind of where my expertise ends a little bit also. So our silicon architect would have to jump in here and explain all of these things even more deeply. But yeah, there's definitely that. And then there's the fabric, right? The fabric is extremely, again, no software involvement. It's a very optimized engine that deals with things like congestion. So that's also in the IP, right? That's really important, actually. And there's PCI Express in there. Yeah, that's pretty much it.
Tell me about who is the target customer for this. Is it the hyperscaler? Is it on-prem? Is it neocloud? Is it sovereign AI? Is it all of the above? Or what kind of customers are you getting traction from already?
Yeah. So we're mostly seeing traction right now with, I guess you would call them neoclouds, small and large. Some are huge, others are tiny, as in neoclouds that have already signed some kind of commitment with us. Most of the time, that's some kind of a pre-order of a system. We definitely also have contractual relationships, I would vaguely call it, with the more traditional hyperscalers. There's S&P 500 companies, and then there's lots of other companies that we have LOIs with. So what I can say is that the first many systems that we'll produce are already all spoken for. They're going to be used in one way or another. We're also going to build up a small data center ourselves, just to give remote access and remote evaluation possibilities to everybody who wants to, first evaluate, try it before you buy it, kind of thing, which is super essential, all right? Because most people are not going to spend that money on an expensive AI box before they can even try it. And we also don't want to ship to everybody physically before they've evaluated it. Most people don't even want that. It's too much of a hassle. Yeah, but I would say, to answer your question, it could be theoretically anyone who owns a data center and buys NVIDIA hardware for inference, right? If they do that, they can definitely also look at us and start to blend in Tensordyne into their otherwise NVIDIA or AMD dominated data center. They will definitely be saving a lot of area, power, money, and they'll be able to get more per user speed out of it. So yeah, could be theoretically anyone, but right now the most aggressive and pioneering companies, I would say, are the neoclouds. Yeah.
Okay, last question then. I think it maybe is a little bit too early to be asking you about kind of multi-generational hardware roadmaps. You mentioned that you are working on the next gen already. Apart from going to a more advanced process node with the LNS, math, and everything, what other directions can you innovate in for those future generations?
Yeah. Networking is huge. Right? Like going even more natively to even bigger scale ups, beyond 1,000 chips and so on. That's that's another kind of area. Technology wise, there's a few obvious things, right? Like you want to go to the latest HBM, you want to go to the latest TSMC node and things like that. But there's also technologies that we might be integrating, at least in that way, for the first time. Could be co-packaged or near packaged optics. Otherwise, we'll try to, of course, keep things as simple as possible in terms of an evolution, because we want to be fast to market, even with the next system, or again with the next system. What else is there? We will also be, you have to be careful about the CPU to AI compute ratio and how exactly that's from a hierarchy designed. Because CPUs, there's going to be a lot of CPU involvement. The more random and bursty AI gets, and more agentic, I guess, if that's not an overused word by now. Yeah, there's going to be a lot of CPU involvement, so that's important. And then the ratios. I think we're gonna, well, not we will, but we have revisited, of course, also the ratios. But what I mean by that is you have AI compute, memory bandwidth, memory capacity, SRAM bandwidth, SRAM capacity, fabric latency, fabric bandwidth. So just these alone, they all have to have a certain ratio to each other. Every ratio between every pair matters. And we have to, just think about, where our model size is heading, right? 10 trillion, 100 trillion parameter models. Our next system will certainly be able to do at least 100 trillion parameter models. So those are the topics. New technologies. Definitely also still evolving our LNS math. That's already almost done by now, so we'll have a third gen of it, basically. Yeah.
Well, very exciting, Gilles. Thank you so much for talking us through it.
Thank you, Sally. It was a pleasure.
Thank you, Gilles. There was a lot of information we haven't heard before. This episode of AI with Sally was brought to you by Tensordyne. Thank you very much, Tensordyne, for sponsoring us. If you want to learn more about Tensordyne, please check the links on the podcast page at eetimes.com. Thank you for listening.